swing equation. We know that in the case of a synchronous machine, we have got two fields. One is the main field, that is what you are calling is the rotor field. This is excited by the external DC source. Whereas there is a stator magnetic field which is rotating with a synchronous speed because of there is a flow of current in the armature conductors. There are three windings, and if the currents they are flowing in the three windings, then there is a rotating magnetic field is producing. Therefore, there are two the fields, that is the stator magnetic field and there is a rotor magnetic field. But in the case of the synchronous machine, that is the name itself suggests that the both stator and the rotor fields they are rotating with a synchronous speed at normal operating condition. Normal operating condition. In the event of loading, then what happens? There is a rotor field, or the rotor is either retard or it is accelerate depending upon the load. Means the angle which is between the rotor field and the stator field, that is what we are defined here is load angle, that is changing because of change in the load condition. If the load is more, the delta is increasing. If the load is, if you are taken off from the system, in the delta is, it is decreasing. Means the rotor field or the rotor is either accelerate or decelerate with respect to the stator magnetic axis. That is before settling down to new value of delta, the rotor is swinging with respect to new equilibrium position, that what you are calling is the swing of the rotor angle, because the delta angle is changing before settling down to new value. At that instant, once again the rotor speed is equal to the synchronous speed. Then the relating the change of swinging of this angle delta with respect to the time is called as the swing equation. The same thing is elaborated in these points here, that is the angle between the rotor axis and the stator axis is called the load angle or the torque angle, that is defined, that is a rotor field and the stator field, that is angle between those two is called as a delta. Under normal operation, load angle is fixed. When if there is no change in the load, then the angle between the rotor field and the stator field, that is fixed, and both are running with a synchronous speed. Depending upon the loading of the machine, larger the loading, larger the value of torque angle delta. If the load is increased, then the ultimately angle delta is also increased. The rotor will decelerate or accelerate because of addition or removal of the load from the shaft. If you are putting more load, it will decelerate. If you are taken off the loads, then it is accelerate. The rotor of the machine decelerate or accelerate with respect to synchronous or rotating stator field and relative motion because. That is because of taking off load or putting the load on shaft, the rotor of the machine is decelerate or accelerate with respect to the stator rotating magnetic field which is running synchronous speed. Therefore, it is said that the rotor is swinging with respect to the stator field, because the value of the rotor, that is speed of the rotor, either accelerate or decelerate with respect to stator. Therefore, it is said that the rotor is swinging with respect to stator field. That is why the equation which is describing the relative motion of the rotor, that is a rotor angle with respect to the stator field as a function of the time, is known as swing equation. That is an equation which is describing the relative motion of the rotor, that is in terms of delta with respect to the stator field as a function of time. That is what we are calling as the swing equation. We know that there is an inherent property of the machines in the event of there is a large changes in the loading conditions, then that is come under the transient stability. Therefore, it is affect the dynamics of the synchronous machines. Therefore, the transient analysis involves some of the mechanical property of the machine in the system, in the form of stored energy, inertia, all those things. That is a mechanical property of the system. And in other part, after every disturbance, the machine must adjust to relative angles of their rotors to meet the condition of the power transfer involved. That is, in the event of there is a change in the load condition, one is the property of the mechanical in the term of the stored energy, inertia, and all those they are affecting. In other words, in the part of the electrical part of view, if there is a change in the load conditions, there is imbalance between the mechanical input and the electrical output, or electrical output and the mechanical input. There is a change in the power conditions and the load angle. Therefore, the problem is it is a combination of both mechanical and the electrical. Therefore, the problem is mechanical as well as the electrical. That is shown in this particular the block diagram. Here I am representing the generator here. There is an input in terms of the power, that is I am putting PS is the shaft power input to the generator, whereas the P is electrical power, the output, the electric power output, where PS is the shaft input, whereas P is the electrical output. Then if the input PS which is greater than PE, then there is a shaft is accelerating, because the input is greater than the output, therefore there is an acceleration takes place. Suppose the same situation we can express in terms of the torque, that is a TS is the shaft torque, that is the input to the generator, whereas the TE is the electromechanical torque output. If the shaft torque TS, which is the input, is greater than TE, that is electromechanical output, which is less as compared to TS, in that case there is an acceleration. Therefore, that is what we are calling is acceleration torque. That is, T is possible only when, that is, input is greater than output. Input is greater than output. Therefore, in terms of torque equation, TA is equal to TS minus T. That is the input minus output torque. That is TA is equal to TS minus T. That is TS is shaft torque, whereas TA is the accelerating torque. However, T is electromagnetic torque. It is electromagnetic, not mechanical. It is electromagnetic torque. Therefore, the shaft torque TS, if it is greater than the electromagnetic torque of a generator, in that case there is a accelerating torque is producing, that is a TA. TA is TS minus T. But in the case of the motor, the input is electromagnetic torque, the output is, that is nothing but a shaft torque. In that case, if the electromagnetic torque which is greater than the mechanical power output from the machine, that is what we are calling as a motor. Therefore, in the case of the motor, our TA will be TE minus TS, because T is the input for the motor, TS is the output for the motor. The same expression can be expressed in terms of power equation, that is, the accelerating power PA can be expressed as PS minus P, and instead of expressing in terms of torque, here I am expressing in terms of the power, that is PA is equal to PS minus P. Similarly, for the motor, it is a PA is PE minus PS. PE minus PS. Then once again we will look into the string equation. Here I am representing the stator magnetic axis. It is rotating with omega r, and rotor field is omega n. The angle between these two is delta. Then this rotor field as well as stator magnetic axis are drawn with respect to a reference axis, such that the angle between reference axis and rotor field axis I am representing by theta, whereas the angle between the stator and rotor fields are delta. Then it is rotating with omega r, therefore theta can be expressed in terms of omega r and the delta. So that the theta, if it is rotating with omega r, then the time taken for to reach at this point is t seconds. Therefore the angle traversed from reference to here is omega r into t, and this angle is delta, that is omega r t plus delta is nothing but your theta. Therefore the theta is equal to omega r t plus delta. This is how we have to find out the value of theta. That is, theta is the total angle from here to here. From here to here, the angle is omega r into t. That is, its speed is omega r. It is the radians per second. Then if it is taking a time t to reach this particular point, then it is omega r into t. That is nothing but once again radians, and t either radians or a degrees plus this delta, that what I am getting is theta. Okay, just for my calculation in the string equation, just I am taking the differentiation of this equation. What I am getting here is taking a derivative of this equation. What I am getting is d theta by dt, that is equal to omega r plus d delta by dt. I am differentiating both sides with respect to t. Further differentiating this equation, what I am getting is d square theta by dt square is equal to omega r is a constant, that is become 0. Therefore d square delta by dt square, this is d square theta by dt square or d square delta by dt square, that is what we are calling as the acceleration, and it is represented by the alpha. That is represented by the alpha. Okay, with this background, then we will derive the string equation. Once again, I am recalling the shaft torque, accelerating torque and electromagnetic torque. Then for generator, TA is Ts minus T, and TA is Te minus Ts for the motor, and for the in terms of power, it is Pa is equal to Ps minus P, and Pa is equal to Pe minus Ps for the motor. Then we know that the power can be expressed in terms of the torque and the angular velocity, as power is equal to torque into angular velocity. Therefore, the angular velocity omega, which is measured in terms of the mechanical radians per second, the angular mechanical radians per second. Therefore, that is equal to omega is equal to 2 pi ns by the 60. Here, the power Pa can be expressed as Pa is equal to Ta into omega, that is the angular velocity. But the value of the angular velocity is 2 pi ns by 60, where ns is the speed in rpm. Then also we know that the torque is expressed in terms of moment of inertia and angular acceleration. Therefore, the torque is the moment of inertia into angular acceleration. That is, the moment of inertia as I, that is what I am putting in this equation. In the torque equation, what I am doing here is, instead of Ta, just what I am putting is I into omega. In the Ta, I am putting I into omega. Therefore, Pa is equal to instead of Ta, just I am putting instead of Ta moment of inertia into omega into angular acceleration. Angular acceleration is alpha. That is Pa is equal to I into alpha into omega. Then I am combining I and omega. That is represented by the value m. That is, I am combining I and omega. I am defining one more term, that is m. That is, m is nothing but I into omega. That is called as the angular momentum. Momentum. That is, we have got an expression for the accelerating power Pa is equal to m into alpha, that is in terms of angular momentum and the acceleration. Just it is very simple. Power is torque into angular velocity, that is Pa is equal to Ta into omega, whereas the torque is the moment of inertia into the angular acceleration that I am substituting in this equation. Therefore, that is moment of inertia is I and angular acceleration is the alpha and original omega is retained as it is here. Then I and omega is clubbed together, then making another constant, that is m, that is called as angular momentum. Then Pa is equal to m into alpha. M is known as the angular momentum. It is usually expressed in terms of megajoule second per electrical degree. It is usually expressed in terms of megajoules second per electrical degree. How we are arrived at this particular the unit for this m, that we will see in the subsequent discussion. Okay, at this point you can remember that Pa is equal to m into alpha, that is angular momentum multiplied by acceleration is the accelerating power Pa. Then with the d square theta by dt square is equal to d square delta by dt square, already we have derived, that is what we are calling is the acceleration. Therefore, Pa is equal to m into alpha. That is already we have defined this, Pa is equal to m into alpha. However, alpha is equal to d square delta by dt square. Just I am putting here Pa is as it is, m as it is. Instead of alpha, that is I can put d square theta by dt square, or Pa is equal to m d square delta by dt square. The equation which is describing Pa and d square delta by dt square, this equation what we are calling is the swing equation. That is, this m d square delta by dt square is equal to Pa. That is this equation, m d square by delta square dt square is equal to Pa is equal to Ps minus P. This is called as the swing equation. The differential equation that relates the angular momentum m, the accelerating power Pa and the rotor angle delta is known as swing equation. It is a relation between, it is a moment of angular momentum, acceleration and accelerating power. If it is a relating accelerating power, the angular momentum and the acceleration, that equation what we are calling is the swing equation. The solution of this swing equation show how the rotor angle changes. If you are finding out, it is the d square delta by dt square, that is the second order differential equation. Then if you are solving for this equation, then you are getting the value of delta at a different time intervals. Then the solution of this swing equation will show how the rotor angle changes with respect to time following a disturbance. Then if you are drawing the plot of delta versus the t is called as the swing curve. That is the equation which is describing m, alpha and Pa, that is a swing equation. And if you are drawing a curve delta versus t, that is called as a swing curve. Once the swing curve is known, the stability of the system can be, that is, assessed. That is, whether the system is stable or unstable, we can the judge based on the deviation of the delta with respect to the time. The another important constant is quite useful in the stability studies is defined by H, and H is defined, it is called as the inertia constant H, that is defined as it is a ratio of kinetic energy at rated speed to the rated apparent power of the machine. This is how we have to define the constant H. It is a ratio of kinetic energy stored divided by the rating of the machine. That is stored energy in megajoules divided by rating of the machine, that is in terms of MVA. That is H is equal to it is stored energy Ke divided by Z. Therefore, if you are taking Z, the left hand side, it is Z into H is equal to stored energy in megajoules. That is, we know that stored energy is half I omega square, that is I omega square, then it is 1 by 2 I omega into omega, that is I into omega